My name is Rajas, and for my project, I chose to do reaction kinetics for differential equations and understanding how chemical reactions change over time. Differential equations have sorry, differential equations have been crucial in all disciplines of science because they illustrate the progression of changes over time. Reaction kinetic analysis, the study of how quickly or slowly chemical interactions change with time, is another branch of chemical engineering, where I chose it based on its mathematical relationships with the physical modeling required for developing optimal reaction conditions or quantifying reactants or products in chemical reactors. After looking at the uses of numerical solutions to illustrate theoretical concepts in both engineering and science, it became clear that I wanted to study in this area of research. At the heart of the reaction kinetics lies the basic type of ordinary differential equation. dA over dt equals negative k times a to the n. The rate of change with respect to time of reactant A can be expressed using the following equation. The K is the constant which measures how fast or slow the reaction occurs, while N is an indicative of the order of that type of reaction. The premise on which this equation is constructed is very simple. However, depending upon the value of the order N, the behavior of this equation will differ significantly from one to another, and this equation serves as a foundation for different kinetic models. As an example, a zero-order reaction maintains a constant decrease in the quantity of material per unit of time. A first-order reaction allows an exponential decay curve as the reaction proceeds, while a second-order reaction will typically decrease according to a hyperbole. The nature of the differences between various order indicates which type of model would work best when predicting how long it will take to complete a particular reaction, or designing a system that will respond safely and correctly, because most introductory course on chemical engineering begins with the use of differential equations similar to this one. Differential equations describe the rate of change over time. All fields use ODEs and their applications are numerous. However, the vast majority of the applications of differential equations occur in the practice of chemistry. A major application of kinetic ODEs is chemical reaction modeling, based on laboratory experiments. Both experimental scientists utilize ODEs in their work for atmospheric reaction kinetics and atmospheric reaction modeling, as well as for modeling pollutant breakdown reactions within the atmosphere and for modeling water treatment processes. There are further uses of relative styles of ODEs, for example, the use of the Michaelis-Menten equations in biological modeling of enzyme breakdowns within organisms. The effectiveness of the mathematical representation of the relationship between kinetic rates of change and the variables within that relationship, that two being ODEs represented by reaction rate ODEs, is very substantive to mathematics as it applies to the natural sciences. Because the reaction rate ODE is a separate class of ODEs to solve, ODEs allow for the student to develop experience in mathematical solving techniques, as well as helping students establish a foundation for understanding real scientific systems through math. Since the inception of reaction rate equations, there has been an interesting and complex process involved in the creation of such equations. The evolution of the modern mathematical approach to studying reaction kinetics began during the 19th century with the work of several scientists who contributed to this area, and two Norwegian chemists, Peter Wage and Cato Goldberg. Besides what is now known as the law of mass action in the 1860s, they inferred that a chemical reaction's rate would depend on the dependency of the reactants on each other in determining how many molecules contribute to the product. At the time, this was one of the earliest known examples of how scientific law could be expressed in terms of differential equation, focused on change. After Wage and Goldberg, the Dutch chemist Jacobus Incus van 't Hoff brought the additional dimension of temperature relationship to the chemical reaction rates. This established a basis upon which future work in chemical dynamics could occur. Van 't Hoff's work ultimately led to him becoming the first recipient of a Nobel Peace Prize in Chemistry in 1901. As advances were made in understanding how chemical reactions occur, scientists began to observe that orders of reaction could not necessarily be correlated with their corresponding stoichiometric coefficients from the balanced chemical equation. This encouraged several scientific contributions, including the idea behind the Arrhenius equation proposed by Savante Arrhenius, and the concepts developed in chain reaction theory by Max Bodenstein. These contributions allowed engineers and scientists to develop a set of models that could be used to describe and predict the behavior of chemical reactions via differential equations. The basic formulation of the ordinary differential equation is fairly simple. However, an individual must have an extensive understanding of both the theoretical and practical aspects of kinetics, both about the physical chemistry or thermodynamics of a reaction that the steps involve each mechanism before being able to correctly use them in their applications. To understand the solution method behind reaction rate ODEs, it helps to derive the general solution starting with the rate law equation of dA over dt equals negative k a to the n. We can solve it using separation of variables, one of the techniques learned this semester. First, rearrange the equation of dA over a or a to the n equals negative k dt. The next step is to integrate both sides. The form of the integral depends on the reaction order of n. So for n equals 0, which is a zero order reaction, we would have the integral of dA equals negative k integral dt, giving us a equals to a initial minus kt. For first order reactions, we have the integration of 1 over a dA equals negative k integral of dt, leading it to be ln of a equals negative kt plus ln a initial. For second order reactions, we would have the integral of a to the negative 2 squared dA equals negative kt, giving us 1 over a equals kt plus 1 over a initial. Through the deviation from each order of reaction, you can clearly see that they produce different functional forms. The method used to develop the solution separation of variables is one of the first methods of solving ODEs that we learned as a class. Separation of variables works very well for the kinetic equations because the rate of any particular reaction is dependent on the concentration of that one reactant. In contrast, however, complicated reaction types such as reversible reactions, consecutive reactions, and enzyme catalyst reactions are likely to require a technique that is more advanced than basic separation of variables, as many of these types of systems may involve system of ODEs, nonlinear characteristics, or approximations such as steady state and pre-equilibrium approximations. As I learned about these more advanced cases, it allowed me to see how the technique covered this semester were a basis for my understanding. However, in practice, real chemical systems often require techniques beyond those currently offered in this course. There is a significant difference between how we learn chemistry in academic setting and how we use experimentation to define the order kinetics of reactions and their rates with the experimental data, while our starting point for solving an equation in mathematics is a well-formulated equation. In reaction engineering, experimentation plays a big role in defining the form of ODE. The combination of experimental and theory results in the ODE associated with reaction kinetics being mathematically important and having real-world applications. When creating the project, I did have questions about the relationship between ODEs and how they are used to describe complex reactions. I noticed that most of the chemical systems described through ODEs involve more than one intermediate step of reaction and often involve multiple catalytic surfaces for all the intermediate reactions to occur. Furthermore, another question that I had was how the uncertainty of the experimental concentration measures impacted the predictive accuracy of kinetic models. Rate constant K calculations are generally made by fitting data and establishing a model with those data points. Therefore, any small error that is produced in the experimental measurements for the concentration would also have some degree of impact on the solution of the ODE. In conclusion, this has provided a very direct example of how differential equations can provide us with an understanding and a means to predict real-life events based on mathematical equations. The ODE equations defining the reaction rates within systems are simple enough to be modeled through the basic techniques discussed throughout this course, while also being complex enough to provide links between important scientific developments and practical uses in various industries. This has enhanced my understanding of how mathematical principles tie in with various engineering disciplines and has opened up many avenues for future study within the area of modeling complex uncertain systems. I believe that ordinary differential equations developed from the rates of chemical reactions are not just academic equations, they will allow for efficient and safe development for a wide variety of chemical processes.